Hello, welcome. Today we are here to learn about Fourier Series, and it is made with love by yours truly, Alchemistics. The point of this presentation is to prove that I did learn it. Also to let you guys have the intuition of what Fourier Series are, because it's pretty cool. And just right off the bat, I'm not going to be proving things completely. This presentation is more aimed to build intuition on what a Fourier Series is. So, big picture, why do we care about Fourier series? And really, it is so we can represent functions as a sum of sines and cosines. So, any function, we can just see it as a summation of sines and cosines. And this is the very foundation of how computers process signals. So, think anything from infrared, sound, noise, anything like this. This is how the foundation of how computers can process really complex things like a squiggly function and actually turn it into something like zeros and ones that it can process. This is also will give us the building blocks of periodic functions. So what is a periodic function? Just like anything that repeats. So to build intuition, if we look at this rather silly looking function, even though it might look complex, I can just tell you right off the bat that this is it decomposed into sines and cosines. So in this case, it's just using cosines, and this function is just these two cosines added together. We can do this for any function, no matter if it looks like a mess. Like for example, like that. This is also can just be a series of sines and cosines. And by the end of the presentation, hopefully that makes a little bit better sense as to how. So to understand Fourier series and functions, it's a good place to start with vectors. Vectors we can intuitively visualize in our heads. We think in 2D space and 3D space, that makes sense to us. So let's go ahead and start with vectors. So here's our basic vector definition. We know this well. And then we have our norm right here. This is going to come back repeatedly. In the R squared space specifically, the norm is going to give us the actual length of the vector. So think Pythagorean theorem, v squared equals v1 squared plus v2 squared are individual components. And yeah, moving forth, this is in the R squared space. Moving forth, again, we're still going to be working in the R squared space just for simplicity. And we'll expand this later into any dimensional space. So we're going to be working a little bit with the dot product. So what does the dot product mean? How do we get it, etc.? So the dot product, in the end of the day, its ancestor of derivation is the Pythagorean theorem. So we're going to see this vector here, W, and this vector, we can basically get two other functions that are up to this vector and force it to be a right triangle. So no matter what direction this vector is facing, there's always going to be two vectors that can complete, quote unquote, this right triangle. And for this sake, we're going to call one side U and the other side V. And just basic Pythagorean theorem of a squared plus b squared equals c squared, we see at the end of the day that this Pythagorean theorem follows. And if we recall, our norm in the R squared space is going to be the length of a vector. And here it is described. So again, this makes more sense of how the Pythagorean theorem applies. So to get the dot product, we are just going to do some math finagling, just expand this. So in this case, our W is just equal to U plus V. And again, this is described right here. And again, this is simple vector. And if you don't understand this yet, you should review a little bit of linear algebra, if you will. Okay, so we have U plus V. That gets us W. So now that we have W, which is these components, we can now just go down the math and we get our first component, u1 plus v1 squared plus u2 plus v2 squared is equal to, and this is going to be right here, our norm of u squared plus our norm of v squared. Now, recall, you might be wondering what happened to the square root. If we look over here, it got canceled out. That's because the square root of a1 squared plus a2 squared, 2 squared, it gets rid of this square root right here, so we don't have to deal with it. And just with a little bit of math, we see right here that things start canceling out. So our u1 squared over here on both sides cancel out, v1 squared on both sides cancel out, u2 squared cancels out, v2 squared cancels out, and we are left with just 2uv1 plus u2v2 is equal to 0. And this is our foundation of our dot product. And what this right here is saying is that if it's true, if this follows, then the vector u and v must be perpendicular to each other. And why? Because we derived this right here from the Pythagorean theorem. And we just basically rearranged the Pythagorean theorem. And this is how we get our dot product. So moving forth, if we want to expand this from the r squared, so the 2-dimensional space, into the nth dimensional space, we know we can just multiply the individual components and add them up. And what our dot product tells us, and this is the notation right here for the dot product. What our dot product tells us is how closely are the vectors u and v related, and how much one vector is in the direction of the other. So think of it. We know that if u and v are equal to 0, that means that they're perpendicular. So in other words, they are not in the direction of each other at all. That's what this is saying. Oh, and this is just a little fun fact that you can know, that if you take the dot product of two vectors of itself, that's the same thing as the squared norm, and it all comes back. Okay, next thing, now that we understand dot product, the next thing I want to build up is a basis. So what is a basis? A basis is a fancy word for the building block of blank space. So the blank space could be the r squared space, so like 2D space. It could be the 3D space. It could be the nth dimensional space, so on and so forth. I think it's all better if we build this up with a little bit of intuition. So let's look at what the natural basis for r cubed is. The natural basis is going to be I, J, and K. And I'm just letting you know this is what it is. There's proofs. We don't got to worry about those proofs. But we can see how each vector in the 3D space can be clearly and naturally expressed with these bases, with these building blocks. So let's take the vector 5, 2, and 9 right here. Well, we know that if we take 5 times the first basis plus 2 times the second basis plus 9 times the third basis, this is just a different way of representing this same vector. We have decomposed 5, 2, 9 into its basis, and we are left with coefficients. And here are the coefficients, 5, 2, and 9. So again, basis, takeaway, they are the building blocks of set space. We can decompose anything in that space into these basic building blocks. Okay, next, let's expand from the 3D space into the nth dimensional space. So here, I'm telling you that the basis for the nth dimensional space, we're just going to keep expanding. So just like, for example, if it was R4, the first one would be 1, 0, 0, 0. Second one would be 1, 0, 1, 0, 0, so on and so forth, until we hit the last one. And if we're working on the fourth dimensional space, we're going to have 0, 0, 0, and the last one's going to be 1. Does that make sense? So just like the 1 kind of keeps traveling down the vector until it hits the very last one. So that's how it works in the nth dimensional space right here. The other thing about the spaces, particularly the other little special thing, that they're orthonormal. And this is a fancy way of saying that the bases are perpendicular to each other. So think in the r squared space right here with just I and j. Look how they make a right angle right there. Or if you want to look further with the r cubed space, so 3D space, r, j, and k, imagine this is 3D space. Notice how in each of these, they're all perpendicular to each other, each one of them. So to prove that, we're going to take the dot product of these bases, and recall that the dot product right here, if it's 0, that means that they're perpendicular to each other. So what we are hoping is that if the bases are different from each other, so say I and j, we're hoping and we expect this to be 0. And indeed that is true. But if it's the dot product of itself, we hope it to be 1. And that is the fancy thing that this function is saying right here. And this is the fancy mathematical notation. You don't really need to know that, but if you want to impress someone at a cocktail party, you can say that you know what a Kronecker delta is. And this makes sense. And it makes sense if we work with an example. So if we want to build some intuition, here it is. So in the case of the dot product of I and j, you can just work through this problem. You'll see you get 0. I and I, you'll get 1. But go ahead, if this still doesn't make sense to you, work at it with I and k, and then j and j, and see what you get. You should get, if it's the same one, the answer 1 in this bottom one. And if it's different, like here, you get 0. So that is what this formula is saying right here. Okay, perfect. Now, that was just important to build more intuition. Now, we have stated before, like let's say I wanted to decompose 5, 2, and 3 in the 3D space into its different building blocks. So we have 5i plus 2j plus 3k, so on and so forth. What is the mathematical notation of that? How can we mathematically represent that? This is what this function is telling us. This function gets us from 5 to 3 into its building blocks. So again, this makes sense better with intuition. Let's start working in the r squared space for simplicity, but this works for the any dimension. So in the r squared space, we have n equals 2. So this n right here is going to become 2, and indeed it does right here. So the summation from 1 to 2 of our vector right here, 5, 2, of our kth basis, so that's our dot product, times our kth basis. So again, right here, we start filling things in. 5, 2, our kth basis for here is going to be 1, 0, because this is our first one, plus our second basis, which is 0 and 1. And if we take the dot product right here, we get 5 times 1 plus 2 times 0 is equal, this cancels out, to 5. Likewise, oh, and this is our first coefficient right here. Likewise, if we take it right here, the second one, we have 5 times 0 plus 2 times 1 is equal to 2. And again, we see this represented. I have purposely left, instead of representing this as 1, 0, I have purposely left them as its vector symbol. Why? So we can better clearly see how we have decomposed our vector through this mathematical formula into its bases. And again, if you want to see it returned back into its normal vector, you can just work your way forwards again. But notice we've decomposed this vector into bases with coefficients. And the other thing I want you to take note of is that our coefficients are represented by this dot product right here. The dot product of the vector and the basis. The kth basis is going to give us the coefficient of that basis. And again, this is very important, so please build the intuition if this doesn't make sense. Work through another example yourself until it clicks. Okay, we finished up with vectors. Now we're moving forward to functions. So functions is going to be the same thought process. But now instead of working in the R squared space or in the R3 space, in the 2D3 space, we're going to be working in a different space. You don't really have to worry about it. The official definition is that this space is any function that's less than infinity if it follows this. All this is saying is that the function has finite energy between 0 and 1. We can think of function as just infinitely dimensional vectors. So instead of yeah. Okay. Now, let's start translating things from vectors to functions. So in the vector, we had our norm here, and we went from squaring each individual component and adding them all up. In the function space, how we translate that is with an integral. So from the integral from 0 to 1, since we are working in the space between 0 and 1 right here, we want to square each individual component, which is within the integral, and this is what this gives us right here. I think this is the hardest part in the slide to make intuitive sense, but take some time, learn it. And now, again, we can apply the Pythagorean theorem with this norm. Now that we have this norm definition, and we have a squared plus b squared is equal to c squared, or like the addition. And again, we work through this with vectors, and we can see the same thing happening. And if, again, we just work our way down and calculate it, we can start canceling things out, and we're left with, we cancel out this 2, we're left with f of t of g of t is equal to 0. And that, again, ladies and gentlemen, is how we get our dot product. This is the dot product definition of real valued functions. Now, for this sake of Fourier series, we need to be working with complex valued functions as well. And all that really changes is that we need to conjugate the second variable. And this is the reason why you can read through it if you are interested. So this gives us the dot product of possibly complex valued functions. Okay. Here's the real meat and potatoes. Just like in vectors, our basis was 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Our basis for functions is e to the 2 pi int. I won't be proving that here. This is very complicated, and it is the work of many mathematicians combined. But if I tell you that the basic building blocks of the function is e to the 2 pi int, I have already demonstrated that any function can be represented as cosines and sines. Because recall that e to the 2 pi int, using Euler's formula, is the same thing as this formula on this right here. And again, you can read through this and to prove to yourself as well that not only is this a basis, but it's an orthonormal basis. And again, we get the same result that we can see right here, where if the bases are equal to each other, we get 1. And if they're not equal to each other, they're not the same basis, we get 0. and you can prove that. The important thing to note is that we did not prove it was a basis. What we did is we proved that it was orthonormal. So moving forth, now that I've told you that this is our basis, we can now make a formula of how to decompose any function in the L squared space into its basic building blocks. So again, let's just follow the formula. The same thing we did for functions. So we know that the dot product of f of t of g of t is right here. It's f of t times the conjugate of g of t. And if we follow that, we know right here, the dot product of f of t of e and t is going to be f of t times the conjugate of 2e to the 2 pi int, which we get from right here, which in this case makes it just negative. Perfect. And this formula right here effectively gives us what we call the Fourier coefficient. Just like if we recall last time with vectors, the dot product gave us the coefficient, so it gave us 5, it gave us 2. Same vibes right here. This is going to give us the coefficient of the basic building blocks, how powerful each block is to the entire function. And now if we put it all together, we have f of t is the sum, the infinite sum, of the Fourier coefficient with its basic building block. And this, ladies and gentlemen, is what gives us the Fourier series. And what this function tells us at the end of the day is that we can decompose any periodic function in this space into a series of sines and cosines. Dun dun dun! Thank you for tagging along on the journey that is Fourier series. Have a great day.